Okay, we are starting the additional practice problems for chapter 10. And I'll say at the outstart that I'm not going to do number 10. I realize that the way that question is written is confusing. So we'll just do questions 1 through 9. And there won't be a question on the test that's like question number 10. Okay, so number 1 says convert 25.0 degrees C to Kelvin. Okay, so Kelvin is equal to degrees C plus 273.15. So it's just going to be 25.0 plus 273.15. So Kelvin will be equal to 298.15. And we're adding here, so we take the least precise value, so this goes out to the 10th place. So it would be 298.2 is the temperature in Kelvin. Okay, number 2. Dry ice has a temperature of 195 K. What is that temperature in Celsius? Okay, so again, K is equal to degrees C plus 273.15. Okay, so now we want to solve for C. So that we're just going to subtract 273.15 from both sides to get rid of it on this side. So I'll subtract that, and we'll subtract it from this side. So Kelvin minus 273.15 will give us degrees C. The temperature in Kelvin was 195. So we'll subtract 273.15. That's going to equal degrees C. And what you should get for that, we can just go out to the ones place here. Because that's all this one goes out to. So what you'll get is negative 78.15 degrees C, but we have to go just to the ones place. So it would be negative 78 degrees C. So 195 Kelvin is equal to negative 78 degrees C. Okay, number 3. A balloon contains 149.6 liters at a pressure of 567 torr. If the temperature stays constant, what is the volume? So this is V1, this is P1, and then it says what is the if the temperature stays constant, what is the volume? So in other words, what is V2 when the pressure is 981 torr? So P2 equals 981 torr. Okay, so if we write out the combined gas law, V1 over P times P1 over T1, that equals V2 over P2 times P2 over T2. And this says that the temperature stays constant. So any of these variables that stay constant, we can just eliminate from our equation. So then we're left with V1 times P1 equals V2 times P2. And for the ideal gas law, you can use any volume unit. I'm sorry, for the combined gas law, you can use any volume unit and you can use any pressure unit. It's just that temperature must be in degrees Kelvin. Okay, so we're asked to solve for V2, so we'll just divide both sides by P2. Gets rid of that there, and then put it over here. So V1 times P1, divided by P2 will give us V2. Okay, so the V1, the initial volume was 149.6 liters. The initial pressure was 567 torr. And then the P2 pressure was 981 torr. Okay, so this is V2. So the pressure units cancel, and we'll be left with liters, which is a proper unit for volume. So 149.6 times 567 divided by 981 will give us 86.5 liters. And we can have three significant figures. So that's our answer right there, 86.5 liters. Okay, number 4. Okay, so number 4 states a gas-filled balloon has a volume. So volume is equal to 15.6 liters. And it's on the ground where the temperature is 25 degrees C, 25.0 degrees C. And the pressure is 1.01 atmospheres. The balloon rises to an altitude where the temperature, so this is T1, T2, it's going to rise to an altitude where the temperature is negative 12.1 degrees C. And the pressure, as it's rising to altitude, we know the pressure is going to decrease. So the pressure is 0.10 atmospheres. And we are asked to find the new volume. Okay. So a couple of things here. Volume and pressure can be in any unit, so we'll just keep those in the units that they are in. You could change them to something else, but you don't need to. However, temperature needs to be in Kelvin. So Kelvin is degrees C plus 273.15. Okay, so for T1, it's going to be 25.0 plus 273.15. So T1 will be equal to 298.2. Going out to the tens place here. Okay, so I'm going to replace this temperature with the temperature in Kelvin. Okay, and then the next one over here, T2, negative 12.1 degrees C plus 273.15. And that temperature comes out to be 261.1. So T2 is 261.1 K. Okay, and again, we're going out to the tens place because of this. Okay, so I'm going to replace this T2 in centigrade with the Kelvin temperature, 261.8 K. Okay, so now that we have the temperature set, now we can solve for V2. So combined gas law, P1 V1 over T1 equals P2 V2 over T2. Okay, so we just want to get that V2 by itself, so multiply both sides by T2. Multiply it, so it's going on the top over there. Those get canceled out there, and then we need to get rid of this P2 over here, so we'll divide by it. Divide both sides by P2, that gets rid of that over there. And then what we're left with then is we've solved for V2. So V2 is equal to T2 P1 V1 over P2 T1. Okay, so then it's just a matter of plugging in the numbers. So T2 is T2 261.8 K times the P1 pressure, 1.01 atmospheres, and then the V1, the volume, the initial volume on the ground, 15.6 liters. And then we'll divide that by P2, which is 1.10 atmospheres, and by T1, which was 298.2. Okay, so let's look at units. So we have a K on top and a K on bottom. We have an atmosphere on top and an atmosphere on bottom. So we're left with just liters, and that's what volume would be. So 261.8 times 1.01 times 15.6 divide by 0.10 divide by 298.2. So V2 will equal 137.957 liters. However, this limits us to just two significant figures. So we would have to say that V2 is equal to 140 liters. That's our final answer. Okay, number 5. How many moles of water vapor, because we have water vapor, that means it's water in a gas form. How many moles are present? So we have 615 milliliter container. The temperature is 21.5 degrees C, and it's at 745 torr. Okay, so for this one, you have to ask yourself, am I going to use the combined gas law for this, or am I going to use the ideal gas law, combined gas law or ideal gas law? Well, we're asked for the number of moles, and the combined gas law doesn't give us a way to calculate number of moles. Okay, so that eliminates that one, and so that just leaves us with the ideal gas law, PV equals nRT. Okay, so that's what we'll use. However, we have to remember a few things. The value for R is 0.0821, and it's liters times atmospheres over mole times Kelvin. Okay, so that means all the other units need to be consistent with that. So we need to convert these milliliters to liters. We'll just divide by 1,000, so we'll move the decimal place 3 places to the left. So the volume is going to be 0.615 liters. temperature needs to be in Kelvin. So the Kelvin is degrees C plus 273.15. Okay, so add that to the temperature in degrees C, and we get 294.7. And this tells us we can go out to the tenths place. Okay, we're adding and subtracting, so we don't count the number of significant figures. We look at the place value. Okay, so that's the temperature is okay. So we got the volume in the right unit. We have temperature in the right unit. Now we need to deal with pressure. And we need to get pressure in atmosphere. And 1 atmosphere, so we want it, we're changing 2 atmospheres, so that goes on the top. And 1 atmosphere is 760 torr. So torrs cancel. You're left with atmospheres, and that comes out to 0.980 atmospheres. Okay, so now we have everything that we need. I'll erase this. I'll put our 0.980 atmospheres here. Okay, so now we have what we need to use the ideal gas law. So PV equals nRT. Okay, and the question asks us to find the number of moles. So divide both sides by RT. So RT cancels over there. So PV divided by RT equals N. Okay, so then let's just plug in numbers. So the pressure was let me slide this over here. I'm going to put this up here real small. PV equals nRT. PV over RT equals N. Okay, so let's plug in numbers. So the pressure was 0.980 atmospheres. The volume in liters, 0.615 liters. And we divide that by R, which will be given to you, 0.0821 liters times atmosphere over mole times K. And then temperature in Kelvin, 294.7 K. Okay, so looking at units, atmosphere, cancel. Liters, cancel. Kelvin, those cancel. So all we're left with is moles. And if we do this math, 0.980 times 0.615 divided by 0.0821 divided by 294.7, I think you should get 0.0249 moles of water vapor. This is what the question asks us for. I'm going to go ahead and run those numbers in my calculator again, just to be sure that I did my calculations correctly. So 0.980 times 0.615 divided by 0.0821 divided by 294.7 equals 0.024910239, but we can add 3 significant figures. That's not a significant figure, so 0.0249 moles gives us the correct number of significant figures. Okay, so that's number 5. Okay, number 6. What is the volume of 100 grams of ammonia? So we have 100.0 grams of ammonia. Ammonia is NH3. At 84.5 degrees C and a pressure of 869 torr. Okay, and what we are asked to find is volume. Okay, we can't use the combined gas law here. We're only given one temperature, one pressure. So that means we have to use the ideal gas law to answer this question. PV equals nRT. So we're given temperature. We'll have to convert it to Kelvin, but we're given temperature. R is a constant. We're given pressure, and we're asked to find volume. Okay, so the only thing that remains is N. We don't know N, however, we know how many grams there are, so we can convert those grams of ammonia to moles of ammonia. And that's what we would plug in for the value N. So before we do that, let's go ahead and change this to Kelvin. So I'm going to add 273.15. So the temperature in Kelvin is 357.7. Okay, again, we're adding, so we can go out to the tenths place. So that's K. And then we have to convert this to atmospheres for the ideal gas law. So 1 atmosphere is 760 torr. Okay, so those are going to cancel. 869 divided by 760 gives us 1.14 with 3 significant figures, 1.14 atmospheres. Okay, and now let's go ahead and figure out N. So here's our equation, PV equals nRT. Okay, so let's go ahead and figure out N. So we have 100 grams of NH3. We want to convert that to moles. So we want moles on top. 1 mole is equal to 17.04 grams. How did I get that? So there's 1 nitrogen in NH3 and there's 3 hydrogens. So the nitrogen is 14.01 and then you're going to have 3 hydrogens, which is each going to be 1.01. So that comes out to 17.04 grams per mole. Okay? So 100 divided by 17.04 tells us that we have, with 4 significant figures, we have that the number of moles, which is N, is equal to 5.869 moles. Okay, so now we have everything that we need to solve for the volume that we were asked to find. Okay, so let's see. Erase some of this, keep the values that we need. Okay, so now we're back to PV equals nRT. We were asked to find the volume of ammonia. So we'll solve for volume by just dividing both sides by P. So V is equal to nRT divided by P. Okay, so then let's just plug in numbers. So Vn is 5.869 moles. Write this up here a little bit. So B equals nRT divided by P. Okay, that's we just solved that for this. So the number of moles is 5.869, and we'll multiply that times R, which you'll be given 0.0821, and the units are liters times atmospheres over moles times Kelvin, and then the temperature in Kelvin, 357.7 K, and then we'll divide that by the pressure, which was 1.14 atmospheres. Okay, so if we look at our units, so here's an atmosphere and an atmosphere. Here's a mole and a mole, and here's a Kelvin and a Kelvin. So the units we're left with is liters, and that is a good unit for volume. So 5.869 times 0.0821 times 357.7 divided by 1.14 gives us a volume of 151.18 liters. But let's see, we can have 3 significant figures. So that, because of this, so that means that our volume would be 151 liters. Final answer for number 6. Okay, number 7. How many liters of hydrogen are made at 25.0 degrees centigrade, 1.12 atmosphere, when 25 grams of magnesium react with excess hydrogen chloride in the following equation? Okay, so let's write the equation up here. So we have magnesium, which is a solid, plus 2 HCl's. That's aqueous, so it means that it's a chemical mixed in a liquid. And that is going to give us magnesium chloride, which is also aqueous, plus hydrogen gas. So H2, they don't tell us it's a gas, but we know it's a gas because it's a homonuclear diatomic. Okay, so it exists like that, and that's a gas. Okay, so this is aqueous, and that one's a gas. Okay, so how many liters of hydrogen are made? Okay, so we want to know how many liters of this are made. Given the temperature, the pressure, and that we start with 25 grams of magnesium. Okay, 25.0 grams of magnesium. So you might be tempted to use Avogadro's law because we're dealing with a gas in hydrogen. However, remember that Avogadro's law only works when you're only working with gases. So it's not going to work because the magnesium is solid. Okay, but you should recognize that we are told about magnesium and we are asked about hydrogen gas, about hydrogen. So that tells you right away that we're going to have to use stoichiometry to get our answer. Okay, so remember that for stoichiometry we need to have everything in gram or in moles. So we need to change this grams of magnesium to moles of magnesium. And then from there we can we can take the steps that we need to ultimately determine how many liters of hydrogen gas would be produced in this reaction. Okay, so magnesium. We have 25 grams of magnesium. We need to get that to moles. So you look at your periodic chart and you see that, so moles is going to go on top because we're going 2 moles. Grams will go on the bottom. When you look at your periodic chart, you will see that there are 24.31 grams in a mole of magnesium. Okay, just get that from the periodic chart. So grams cancel, and you are going to be left with moles of magnesium. And with 3 significant figures, it will be 1.03 moles of magnesium. Okay, now that we have moles of magnesium, we can use that to determine moles of hydrogen gas. So 1.03 moles of magnesium, and we want to know how many moles of hydrogen gas. So the ratio is 1 to 1. So there's 1 H2 for each 1 magnesium. Okay, so the magnesium cancels, and 1.03 times 1 divided by 1 is equal to 1.03 moles of hydrogen gas. Okay, so now we have the moles of this, but we want to know liters. So you can use the ideal gas law to get there. So let's erase this. Remember that 1.03 moles of hydrogen. So we'll write that up here. So we had 1.03 moles of the hydrogen gas, but we want to know how many liters. Okay, so PV equals nRT. And we want to know how many liters, so we want to solve for volume. So we'll divide both sides by P. So what we have then is that V is equal to, so the P's cancel here, V is equal to nRT divided by P. Okay, so then let's look what other variables were we given. So we were told the temperature was 25 degrees C. So you gotta convert that to Kelvin. So you're gonna add 273.15, and that'll give you 298.2 K. Okay, so that's going to be our temperature, and then pressure. We were given the pressure the pressure is already in atmospheres. No, is that right? Yeah. So the pressure is 1.12 atmospheres. Okay, so we're okay on that. Okay, so I think we're ready then to figure out the volume of hydrogen. So volume is equal to the number of moles, which we determined was 1.03 moles. I'm going to scoot this over so I make sure I have enough room. Okay, so volume, number of moles, 1.03 moles times R, the ideal gas constant, 0.0821 liters times atmospheres over mole times K, and then the temperature in Kelvin, which we just calculated here, as being 298.2 K, and then we'll divide that by the pressure, which was 1.12 atmospheres. Okay, so we'll erase this and just get that out of the way. So let's look at units. So we have a mole here. Oh, good. We have a mole here and a mole there. We have atmosphere here and atmosphere there. And we have K there and K there. So the only units we have left are liters, and that's what we would want volume to be. So 1.03 times 0.0821 times 298.2 divided by 1.12 atmospheres, and what you will get for your volume in liters is 22.5148 liters. And it looks like we can have 3 significant figures. So our final answer would be 22.5 liters. Okay, so the liters of hydrogen gas, which is what we were asked to find. So this reaction, proceeding this way, would produce 22.5 liters of gas. Okay, so all we started with knowing was we started with the number of grams of magnesium. We were told what temperature and pressure we were working with, and then we used stoichiometry and the ideal gas law to determine the volume of hydrogen that was produced. Okay, number 8, next to the last one. A bacterial culture that's isolated from sewage produced 46.1 milliliters of methane gas and it tells us that this was at 25 degrees C and 780 torr. What would the volume of methane be? So this is what we started with under these conditions. What would the volume of methane be at STP? That's what they're asking us. That's our question. Okay, so you need to know what STP is, we said that STP stands for standard temperature and pressure, and the standard temperature is 0 degrees C, and the standard pressure is 1 atmosphere. Okay, so what they're asking is if this is the volume of the methane gas at 25 degrees and 760 torr, then what is the volume of gas at 0 degrees C and 1 atmosphere? Okay, so this is just a combined gas law. P1 V1 over T1 equals P2 V2 over T2. Okay, so the volume can stay in milliliters for this, but the temperatures have to be converted to Kelvin. So this is T1, and to convert to Kelvin, we're just going to add 273.15. So this is T1, and this is P1, and so that temperature is 298.2 K. Okay, and then we can go ahead and convert this 780 torr to atmosphere, since we have the standard temperature and pressure in atmospheres. So, I mean, you could convert the atmospheres to torr. It doesn't matter, but we'll just go ahead and stay with atmospheres. So, 1 atmosphere is 760 torr. So P1 would then be equal to I guess we 1.02 atmospheres. So that's one more significant figure than we should have. So technically, it's still just 1.0 atmospheres. Okay, so that would be our P1. Okay, then P2 is 1 atmosphere, and T2 is 0 Celsius, so we just have to add 273.15 to get that. That's T2 in Kelvin. Okay, and we were asked to find what volume of methane. So we want to know what is P2. Okay, so we're going to solve this equation for P2, and we'll do that by multiplying both sides by T2. So multiply this side by T2, and then divide both sides by P2. So I get rid of the P's over here, and divide this side by that. Okay, so what we have then is P1 V1 times T2 over T1 P2 will give us V2. Okay, so let's plug in numbers. Okay, our initial pressure was 1 atmosphere, P1. We converted this 780 torr and we got 1.0 atmospheres. So 1.0 atmospheres. Our initial volume was 46.1 milliliters. Our T2 was the standard temperature, which in Kelvin is right here, 273.15. So it was 0 plus 273.15. I'll erase that now and get rid of some of that. And then our T1 was 25 degrees Celsius, but that's 298.2 Kelvin. And P2 was 1 atmosphere. Okay, so again, we have an atmosphere on top, an atmosphere on bottom. I got to write K in here for this temperature. So this would be K. So we have a K on the top. Should be 292.2. K, 298.2. Sorry, I didn't, well, this is the number we're looking at, 298.2 K. Okay, so atmospheres cancel, the K's cancel, you're left with milliliters, so your volume will be in milliliters. So 1.0 times 46.1, well, it doesn't matter. Yeah, so times 46.1 milliliters times 273.15 divide by 298.2 divide by 1, and with our answer in milliliters, you should get, with 2 significant figures, you should get 42 milliliters. Okay. You could have changed this to liters. That would have been okay too. But it's okay to, it's also okay for this, for the combined gas law, it's okay to keep it in milliliters. Just going to check my math. Yeah, it's 42.227 milliliters, and we can have 2 significant figures, so it's 42 milliliters. That's number 8. Okay, number 9. What is the volume of 16 grams, 16.1 grams of chlorine gas. Okay, so here's where you need to go back and remember that chlorine is a homonuclear diatomic. So the abbreviation for chlorine is that, but chlorine is a homonuclear diatomic, so it has to be CO2. That's chlorine gas. And the pressure is 1 atmosphere, 1.00 atmospheres. And the temperature is 25 C, 25 degrees C. Okay, so again, when you're given something in grams, that tells you that you should solve this using the ideal gas law, because the ideal gas law is PV equals nRT. Okay, we're given pressure is 1 atmosphere. We're given the temperature in Celsius, but we can convert it to Kelvin. R is a constant, and with the grams of chlorine, we can get the moles of chlorine, and then so then we only have one unknown, and that's volume, which is what we were asked for. Okay, so let's start by converting those 16 grams of chlorine to moles. Okay, so 1 mole is, so it's chlorine, so it's 2 Cls. And chlorine is 35.45, I believe. Yeah, no. Yeah, it is. 35.45, so 2 of those, so 2 times 35.45 will be 70.90, okay, grams per mole. Okay. Yeah, so we'll put 70.90 grams per mole here. Okay, so grams are going to cancel. 16 divided by 70.90 will give us 0.227, with 3 significant figures, moles of chlorine gas. Okay? Okay, so let's circle that. That's one value that we're going to need. And we have our pressure right there. Let's go ahead and convert this temperature to Kelvin. So we're just going to add 273.15 to 25 and get 298. We're adding, and this goes out to the ones place, so we can just go out to the ones place. So even though this will come out to be 298.15, we can just go out to the ones place, which is going to be 298K. Okay, so there's our other value, and R is a given. Okay, so we are solving for volume. So PV equals nRT. The question asks us the volume of chlorine gas, so we'll just divide both sides by P, so that the P's cancel on that side. So V is equal to nRT divided by P. Okay, so N we figured was 0.227 moles. R is the ideal gas constant, 0.0821 liters times atmospheres over moles times K. And then temperature was 298K. And we'll divide that by the pressure, which was 1 atmosphere. Okay, so let's look at units. So here's moles on top, moles on bottom. Here's an atmosphere on the top, an atmosphere on the bottom. There's a K on the top and a K on the bottom, so we're left with liters. So the volume in liters will come out with, looks like 3 significant figures. It will be 5.55 liters. Okay, and again, I'm going to run those numbers just one more time to make sure. 0.227 times 0.0821 times 298 divided by 1. 5.55373666, but with 3 significant figures, it would be 5.55 liters of chlorine gas. Final answer, right there. Okay, so we're not doing number 10. So that is it for the extra practice problems for chapter 10.